A while back, we got this complete Sun SPARCstation IPX system from a viewer who kindly donated it. We've been waiting for the right time to restore it, and having never powered it on, we have no idea if it works or not. The IPX is in the lunchbox format that we've seen previously with our Spark Classic restoration, and the IPX is in the middle of the lunchbox trio. It was released in 1991, with the IPC before it in 1990, and the Classic released 1 year later in 1992. And our goal is to get the complete setup working, including the external SCSI CD-ROM drive. But as you'll see later, we definitely run into some issues along the way. We were eager to actually try it out though, as it would be amazing if we hooked everything up and it just worked. But of course, we're not that lucky. The CRT definitely didn't sound healthy and actually shut off by itself after a bit, and we have no activity out of the IPX. So let's check out the IPX first. The lunchbox form factor is super easy to work with, and opening the system reveals we do have a populated memory bank, as well as both a floppy and hard drive. On the motherboard, we see the Ytech Spark 40 MHz CPU, along with the NVRAM that has external batteries attached to it. Well, sort of attached. There's some neat PCB art, and it otherwise looks really clean. The EEPROM is from 1991 when the system was released. And we did find a little guy that had been living here a while. The power supplies in these systems are known to fail, something we have first-hand experience with when we restored our Classic. Once the two halves were separated, we worked on getting the power supply removed. Aside from two screws, the power supply chassis is held together with clips. And getting the PCB out is relatively straightforward, as nothing has to be desoldered, which makes servicing so much easier. The power supply itself is made by Sony, and it's called the APS-02. It's certainly not in horrible shape, but it definitely needs some help. I'm not sure if this brown goo is electrolyte from the cap, but it's pretty gross. And on the bottom, there's a lot of corrosion and more brown goo, so that will all have to be cleaned up. Before we get started on that, it's worth mentioning there are several solutions out there for these power supplies. Failures are quite common, so you can use something like a Pico PSU as a replacement, and someone even designed an entire replacement board using modular supplies to replicate the voltage outputs. But let's make it harder for ourselves and see if we can actually fix this one. The primary fuse is good, and we don't measure any shorts on the voltage outputs to ground. The bridge rectifier also seems to be intact. Powering it up on the bench, the linear power supply circuit is working. We see 163 volts DC. We have absolutely nothing on the secondary side though. I checked some traces to see if the corrosion had broken any, but they all seem to be okay. The transformer also seems to be okay, but we'll have to check it in more detail later. There is a 12-volt relay on the primary side, so I tested that using the bench power supply, and it sounds good. The optocouplers here are used for feedback, and if they aren't working, the supply won't be able to regulate. I applied bench power to the LED side, which acts to turn on the base of the phototransistors, meaning the collector to emitter junction is now on, and both of them look good. And the switching MOSFET test as expected on the meter. With nothing obvious, I decided to go ahead and remove the capacitors and other components since we know the caps have to be replaced, and the board definitely needs to be cleaned. With the transformer out, I used a ring tester to ensure the transformer windings were intact, so that's great news. And this is the controller board, and it's completely encased in black epoxy, making it impossible to troubleshoot, so we'll definitely need to get that off somehow. And with everything removed, we can see just how gross the board is. I dropped the controller board in acetone to soak for a while and then put the power supply board in the ultrasonic cleaner. We're left with a beautiful board, although you can see where presumably the capacitor electrolyte took off a top layer of the PCB, and we have a lot of exposed copper and some remaining corrosion on the bottom. After soaking the controller board literally for days in acetone, it finally degraded enough for me to get enough of it off to see what was underneath. Unfortunately, the controller chip is difficult to read, but with some Photoshop enhancement, it looks like possibly a Mitsubishi logo and M51978, and then maybe P? After some digging, this turned out to be the Mitsubishi M51978FP controller. Comparing it to the enhanced image, it looks like a match. With that identified, I wanted to make a schematic of this board for myself and for others that may want to repair these in the future. I first made a footprint in KiCad of the controller using the datasheet as a reference. Then I used the multimeter to ring out the board, and constructed the controller board schematic measuring values of components as I went. And here are the results. So I was able to ring everything out and figure out exactly how this controller is implemented onto the board. And I had to desolder a few of the passive components just to be able to get the values, but otherwise it was relatively straightforward. And so this schematic is nice because if anyone wants to be able to repair one of these in the future, or maybe just recreate this board, they should be able to do so with this schematic. And importantly, I got the pin out for connecting the daughter board to the main power supply board and kind of the functions there. And so I wanted to just step through the data sheet and kind of get an idea of exactly how this works. I'm not an electrical engineer by any stretch, and there's a lot of this stuff is still very new to me. And so really this is an exercise for my benefit and maybe yours as well. Here's the data sheet for the M51978FP. And we have the 16 pin variety on the daughter board. I was able to take a look at this and then scroll down here to the block diagram. So from what I understand, a popular way of designing a controller like this is to use something called a totem pole driver. So what we're trying to drive is the gate of the switching MOSFETs. So we need to open and close the gate of the MOSFET in order to switch the transistor on and off very rapidly. And the way this controller works is the oscillator here is what sets the frequency of the switching. And so it uses values from CF, T on, and T off. Those are 3 different pins on this controller. And those lead to a resistor, 2 resistors and a capacitor. Basically, we go through the oscillator, go through this protection, and then we get to this gate here. And these are 2 NPN transistors, and we have our 3 pins here. We have a collector, we have the midpoint, which is the V out. And so this pin will connect to the gate of the MOSFET. And then we have our emitter, which I think should just be tied to ground. So the way this works is that our collector here is just going to be tied to VCC. And this logic here will either switch so you can see here we have the bases of these transistors coming out of this logic. And so if it wants to drive the MOSFET on, it'll activate this base here. It'll drive this base, which allows the current here from the collector to come through here into the transistor and to V out. The flip side though is that if we want to switch that off, then we shut this base down and then we drive this base. And what that does is that if this is tied, this emitter is tied to ground, it just pulls the gate to ground potential. And so it shuts it off. If this controller is not working, we're not going to have any switching. And so I think this is exactly where the problem is. And I'll show you exactly where it is in just a second. So here is an application example of a flyback regulator, which I believe that's what this type of supply is. So we have our T on, T off, and CF pins, and we have the R on here, this resistor, we have R off, and then we have CF. And actually right down here, we have some formulas where we can actually determine the period of the on time and the off time of the oscillator. If we plug in the values for the resistors and capacitor that we have, we end up getting 130 kilohertz. So I believe this oscillator is running at, or is supposed to run at 130 kilohertz. So going back here, I actually went ahead and created a schematic for the primary side of the power supply as well. So if I move up, we can see what that looks like here. And I did this because it's just not very complicated. It really didn't take me nearly as long as I thought it would. Let's see, I've broken this up into a couple of sheets just to make it a little bit easier and to be able to fit everything on one page. So we have the IRF BC40, which is our switching MOSFET. And this is our source, this is our gate, and then this is the drain. This right here, I believe the 75 ohm resistor, yeah, is for our current monitor. So this goes to the current limit monitor pin that goes to the Mitsubishi controller. And then we have a 0.22 ohm resistor that goes to ground. And then we have our V out here, which is the kind of the middle of our totem pole. And that goes to the gate, of course. So when I was originally looking at this with the meter, I heard a short between pins 1 and 2. So if I were to probe 1 and 2 right now, we see a resistance of 0.8, which is not technically a dead short. So it's very close to 1, but for example, if I were to leave this on pin 2 and then probe right there, yeah, so now we have a dead short. So you can see on the multimeter, we're reading 0.1, 0.2 ohms, which is a completely solid short. But if I were to move over here, that goes up slightly. And then if I move over to pin 1, now it's a dead short. So you can see that there, if I were to switch the meter over to continuity mode, of course, I'm gonna hear a beep, right? But in resistance mode, I'm looking at it, yeah, so we're right under 1 ohm. And so my concern is that this controller is actually damaged internally. But the issue is that this controller is very old, is no longer produced. Now there are some on eBay, so I can get a replacement pretty easily, I think. But the other issue is all of this potting compound that's still on the board. And I'm sure there's quite a bit under this IC itself. And so using hot air, I'm not super confident I'm going to be able to get it off of the board without either like lifting a pad or like damaging something. But I'm going to try it anyway. Oops. And so going back here, one of the things we saw was that we were getting a very low resistance between collector and V out, so pins 1 and 2. And that is definitely a problem. So if we go back here on the data sheet and look at the block diagram, we can see that this V out, of course, is at the middle of our two NPN transistors. And so if the collector is shorted to V out, that essentially disables this transistor completely. And of course, if this transistor is not working, we're not able to drive the gate of the MOSFET. And so when I saw this, I realized that, okay, I really need to check it on the actual IC itself just to make sure that that's where the short is. Because if this transistor failed internally, then this controller is completely dead.
So if I probe pins 1 and 2 using the multimeter in the continuity mode, we have the same short. So this controller is definitely dead. So where does that leave us, and what does this mean? Well, I don't really want to try to repair this board, and I also don't really want to remake this board. This controller is no longer available. I mean, besides getting it off eBay, and it just seems like a better solution would be to design something for a current in production controller. And I think it should be doable. I mean, as far as I understand, these supplies are relatively straightforward. It's not like an exotic design or anything. And I think I have an idea for a controller that might work. The problem is I've never done anything like that before. So I'm gonna have to get some help from a friend that knows a lot more about this than I do. And hopefully together we'll be able to come up with a solution that will work with this power supply. And the idea is that obviously I want to repair this supply, but I also want to make this easier for others in the future so that they don't have to go through all the trouble that I did in order to try to get these supplies repaired, because these do fail pretty often and replacing the caps doesn't always work. And so if this controller failure is common, which I have no idea if it is, but if it is, then that means that coming up with a new design and a drop-in replacement could actually be really helpful for other people. So I think I'm going to give it a shot and we'll see what happens. And it's done. I decided to try to implement the UC3844 controller for this power supply. And the 3844 is a very common controller, and it's going to be in production for the foreseeable future as far as I know. It's used in both DIY projects and like production equipment. So I think it's a decent choice for this, and it has a very similar architecture to the Mitsubishi controller that the power supply originally used. And so I had to get a lot of help from my friend Saul Samet. So shout out to Saul for helping me out so much. And he was able to kind of figure out the schematic and get it implemented into the existing design. I wanted to take a look at a couple of things here just to kind of go over the basics. So here's the data sheet, and right off the bat, one thing that's I think a little bit different with this controller is that it's a true current mode controller. And so I think the Mitsubishi maybe technically is a voltage mode controller. I'm not totally sure about that, but as far as what I understand about this one, it uses a current sense and actually implements that into the regulation in a way that the Mitsubishi chip does not. And so we designed it for the 14-pin chip here. And you can see like the pinout is a little bit different, but a lot of it is the same. So down here at the block diagram, we get an idea of kind of exactly what's going on. So the output compensation pin here is definitely different than the Mitsubishi controller, but it uses a totem pole output. So we have the same 3 pins here that we would on the Mitsubishi. So we have the collector here, we have the middle, which is the output, and then we have our power ground. And I think it actually references totem pole up here. Yeah, so we have a high current totem pole output. So one thing that's a little bit different is that we see here that our oscillator frequency is guaranteed at 250 kilohertz, which sounds great because we know that the Mitsubishi one was supposedly running at 130 kilohertz. So that sounds great, right? But down here at this oscillator frequency chart, you can see that the output switches at half the oscillator frequency. Whereas with the Mitsubishi controller, the oscillator was 1-to-1 with the output. So if the oscillator was at 130 kilohertz, the output is going to be 130 kilohertz. But that's not the case with the 3844. So if we wanted our output at 130 kilohertz, that means the oscillator needs to run at 260 kilohertz. And scrolling back up here, we can see for the UC3844 and the frequency here, that the typical frequency is 250 kilohertz, and we saw in the blurb at the top that that's what it's kind of like guaranteed for. If we're going to try to run it at 260, that's above what they say is kind of guaranteed. And so we thought that, hey, let's try to run this a little bit slower, and I think everything should be okay. So we decided on 236 kilohertz, which should give us an output frequency, I think around 118 kilohertz. So the other difference that this controller has is that the duty cycle is a little bit lower than the Mitsubishi. So I think the
Mitsubishi can run above 50% duty cycle, whereas this one is going to be 48 or probably actually a little bit less. And so I'm not really sure exactly how that's going to impact the operation of the supply, but we may have to play around with some values to figure out exactly what's going to work best. So switching back here to the schematic, the frequency for the oscillator is actually set by R4 and C3 here. So we have R4, which is at 22K, and then C3, which is a 330 picofarad cap. And the idea behind this is that it's supposed to be a drop-in replacement. So it should be pin-to-pin compatible, and the only thing we need to change are just two resistors on the main power supply board. And those two resistors are going to be R108 and R107. So R108 gets changed from 75 ohms to I think 390, and this is for the current sense pin on the new controller. And then that's also related to R107, which gets changed from 0.22 to 1 ohm, and that's a 2-watt metal oxide type. And here's the PCB layout for the new board. And this was a little challenging because the physical space that the board needs to fit into is pretty constrained. And you can see the original one is quite tiny. So there were some space constraints that we had to work around, and we're using all surface mount components other than this one electrolytic cap here. But that should be pretty small, and it's at the top, so I think the clearance should be totally fine. And here's the board in the 3D viewer, just to give you kind of an idea of exactly how it's laid out. And I was really thankful to find out that the pitch of the pins on the original board are actually 2.54 millimeters. So if you've ever designed anything in electronics, especially if you've used like Arduinos, anything like that, you know that's a perfect size for a pin header because that's the exact pitch. And so for actually connecting this to the board, I opted for just a right angle pin header. And I tried to source the original style pins that were on the original board, this style right here. And shout out to the Serial Port Discord, as they were able to actually figure out what these pins are. But I wasn't actually able to find them for sale anywhere, and you could only get them in like rolls of 1,000. So the pin header is a way better solution for that. And I think it's going to work out totally fine. I think the next step is going to be getting the boards and trying to get one of these built. And just like that, we have boards. So I haven't actually opened this yet, and I got these from PCBWay, not a sponsor. I wanted to go ahead and unbox these on camera just so we could take a look at them and hopefully just go ahead and get one built and pop it into the supply and see if it works. All right, so let's get the box open here. So I got 5 boards, and that's just because I wasn't totally sure whether this was going to work. And so if this does end up working, I will probably order more because I think this is something we would like to offer as a kit for anyone that needs to repair one of these. So let's take a look here. Wow. Yeah, so these look great. I have all the parts ready to go in, so I think that we should just go ahead and try to get one built. Yeah, let's get started. With the new controller built, we could get started on installing the new caps.
There's actually one more problem. The footprint for the main filter capacitor is not really standard. And for comparison, the original cap is here on the left and the replacement on the right. And you can see how the terminals are oriented in a different fashion. So this presents a little bit of an issue. And I think what we're gonna have to do is actually drill through the circuit board itself. Thankfully on this board, the traces for the capacitor are nice and thick. So that's gonna make it a lot easier when it comes to drilling. Now I should also say I've never drilled through a PCB before. So this will be a learning experience, and I think you simply just drill through the board, expose some copper, and then I can solder to that. So off to the shop and see if we can get this modified.
I reinstalled the rest of the components and touched up the soldering that was near the corrosion. I installed the new resistor values for the new controller and then the new controller board itself. Okay, so I think we are ready to test, and I wanted to kind of go over the test setup because I've got a lot going on here, so I wanted to explain everything. Currently, I have the power supply here, obviously, and I have the oscilloscope here connected to the V-out, which is the gate drive for the MOSFET, and that's going to be monitoring the frequency, the duty cycle, and then the voltage. And so I put those measurements in, and I think I've got the time base and the voltage scale set up correctly for that. So we're gonna see that and just make sure that our frequency and duty cycle are about where we expect. And then on the secondary side, I've got an 8 ohm load hooked up here to the 5 volt output. And I had to solder in just a little wire here just so we could connect everything. And then I'm monitoring that with the multimeter here set in volts DC. And then I've also got the 12 volt fan hooked up here just so we have like a visual indication of the supply working other than the voltage. And I've got the supply hooked up to my isolation transformer, and the oscilloscope is actually battery powered right now. So I got one of these recently. It's just a USB power pack. So I wanted to give this a shot to see if this would work with the oscilloscope, and it does. It has a 140 watt output, which is way more than what the scope needs. And yeah, it works great because whenever you're measuring anything on the primary side of a power supply, it can be a little dangerous. Even though we have the isolation transformer, this just gives kind of an extra layer of safety. So there's absolutely no way, you know, if like a probe clip came off or something happened, you know, the scope is going to be totally fine. So with all that being said, I think we should go ahead and give it a shot, and I'm really hoping that everything just sort of works. So I'm going to go ahead and turn on the isolation transformer, and if it does work, we should see 5 volts here, and then we should see the fan spin here. So let's give it a shot. Okay, it's not working. Yeah, so we've got the voltage fluctuating here. This is on the output. So it looks like it's in a hiccup mode. And looking over at the oscilloscope, oh yeah, our frequency is very low. So it's at 97, around 97 kilohertz, 98. Duty cycle is like 1.3. So yeah, something's definitely not working right. So I'm going to go ahead and shut it off. Okay, so now I want to monitor VCC. So that's the power input for our controller, because if something's going on there, obviously the controller is not going to be able to switch. So let's see, I think it's looking at the schematic. Okay, so it should be pin 6. So 9, 8, 7, and then 6. So that should be okay there. And then on the scope side, we've got 5 volts per division here, and I'm in a roll time base now so that we can kind of see the changes in VCC. Oh yeah, look at that. That's hiccup. So we're going up to the turn on threshold for the chip, and then it's unable to sustain VCC. So it's just hiccups every second or so. So I wanted to take a look at exactly how this startup circuit works for the controller. So we're looking at the schematic that I made for the primary side of the power supply. And here's the controller, and of course this is for the old controller, but the pinout for the new one is identical, so we can still use this symbol here. So we have our B+ voltage here, which comes off of the linear power supply, and that's about 163 volts DC. And VCC here, which is pin 6 on the controller, gets its initial power from B+, but through these two 100k ohm resistors. So if we open up the calculator here and take 163 volts DC, we divide it by 200k ohm, we get, yeah, so 815 microamps, so not even a milliamp that this source here can provide. So we've got the VCC pin here, we've got the voltage and current coming off of B+ here, but it's nowhere near enough to actually run the controller. So we have a startup capacitor here, so C109. What this does is it charges up from this source here, and the voltage slowly increases for VCC. And so that's what we were seeing on the oscilloscope. So we had that nice ramp up to, I think, around 15 or 16 volts before the controller clicked on, and then it dropped down. And so what's supposed to happen is that this startup cap actually just gets the controller going. And then if we look at VCC, we also have a junction over here to a 12 volt regulator, which is the 78L12. And if we look here, the input for the regulator is actually off of this auxiliary winding, so pins 5 and 6 on the main transformer. When this controller switches on, it's going to start switching. So our V out here, which we took a look at on the scope as well, will start driving the gate here of the IRF BC40, our switching MOSFET. So this gate is going to start switching, and then that's going to energize the primary side of the transformer, including the aux winding here. And so it'll come up through this diode down here into the voltage input of the 12 volt regulator. and then our volt, and this is going to be somewhat higher than 12 volts. And then our output is going to be a regulated 12 volts, which is going to come through here through this diode to VCC. And so if there's something wrong with this side of the circuit, the controller is never going to be able to sustain VCC. It's not going to be able to stay turned on. And that's kind of exactly what we were seeing with this kind of hiccup mode, as they call it. So we were getting this cap charging up, and then as soon as it reaches the threshold here, this controller switches on. And that's when this 12 volt regulator, because of the switching action here and through the aux winding, is supposed to take over and provide power. And so on the datasheet for the 3844, we can actually see the startup threshold here. So so min typical max and the 3844. Min is 14.5, so between 14.5 and 17.5 volts, it should switch on. So that's the startup threshold. But then what happens is that it has a minimum operating voltage after turn on. So in other words, it doesn't need to always have 16 volts. And in this case, it just needs 10 volts to be able to sustain operation. And so that's why the 12 volt regulator is totally fine to provide VCC for the controller. And so I think what's going on is, obviously we have some type of issue going on, right? We can't sustain this 12 volt. So instead, what I think we should do is for D107 here, we can lift the anode, which is connected to the aux winding, and we can use the bench power supply to inject voltage there, which we know will be solid and stable, and that should give us a nice 12 volt output for VCC, and then we should be able to get a better idea of exactly what's going on. And so obviously, like if we're providing, I don't know, like 15 volts here for the input, and we're not getting any output, well, there's something going on with the 12 volt regulator. But if everything starts working, then there's some other areas we need to take a look at. Okay, so I've got the diode here pulled up. So I've got it desoldered, so that's the anode, and that was connected to the aux winding side. So we're going to hook up the bench supply here and inject 15 volts and then kind of see what happens. So I think at first we'll just go ahead and turn on the supply to make sure we have the same behavior as before. Okay, yeah, so we're seeing the hiccups here on the output and obviously here on the scope. So I'm gonna go ahead and turn on the bench supply. Whoa! Oh, it's still not working right. So our 5 volt is only at 3.6. We did hear the relay click. Our fan is sort of spinning. And yeah, looking at the scope, we're not doing great. So let me get the measurements back on here. Oh yeah, so we're at 96 kilohertz and only a 5% duty cycle. So that explains why we're having this low voltage, because something's causing the power supply not to run at its set frequency and duty cycle. And so we're gonna have to track that down to figure out what that is. And the two possibilities I could think of was something going on with the compensation network, which is here, so that's on pin 1, or the current sensing on pin 5. And the compensation is driven by a couple of optocouplers here, so this is feedback from the secondary side. And the datasheet actually has a graph showing the compensation pin voltage versus the current sense input threshold voltage, meaning at what point the current sense actually activates, at what voltage level. So we can see that if the comp pin is low in voltage, that means we have something going on there because the current sense threshold is much lower. However, if we're at the normal voltage, which it looks like it's probably around 5 volts or so, then our current sense input threshold should be around 1 volt, which I think is what's considered normal. So I would say let's go ahead and check the voltage at pin 1 to see what we get there. So I'm gonna go ahead and turn this on. And I'll turn on the voltage injection, and Okay, there we go. Yeah, so we're way up there. Let me look at our voltage here. It's way up there, so I think that's okay. Okay, so now we want to look at the current sense pin, which is pin 7. So I'll get that set up over here. Let's go ahead and turn it back on. And then, oh, we are getting some pulses here. Let's turn this to normal. Oh yeah, wow, okay, so our peak is at 1.25 volts, so I think that's definitely going to trigger the current limiting. So maybe that's our culprit. And so to test this, I think what we can do is actually just ground this current sense pin, and that should disable the current sense entirely because it'll prevent that 1.2 volts from showing up there. And so if it's grounded, it just appears to be 0 volts. And so we shouldn't have any current sensing, and hopefully that will give us a little bit more information about what's going on. Okay, so I've got to run the supply on its side just because of how everything has to be hooked up. So I've got the current sense pin desoldered here on the bottom, and then I've tied it to the hot ground heatsink here. And then I've got, of course, everything else set up, and I have the scope monitoring V out the gate drive so we can see the duty cycle and the frequency. And of course I've got the 8 ohm load on the 5 volt, and I've got the multimeter monitoring that. Okay, so I'm going to go ahead and turn on the main supply now. Oh yeah, it's like, you can see it trying to start. The duty cycle is much longer. Oh, it's like, oh, it's still not right. Okay, but we did see our output go to 5 volts, and I don't know if you could hear, but there was a lot of high frequency noise. So I think maybe that's just all the, maybe like some type of limiting going on, and it's just rapidly switching, and maybe that's what's causing that noise. But let me try this one more time. So we turn it on. Yeah, we have 5 volts. Something's not quite right with that. Well, very not right with that. At this point, I decided to bench test the controller board. I desoldered the resistor and capacitor that set the oscillator frequency and empirically selected a combination that provided closer to 130 kilohertz. The 3844 can vary quite a bit in frequency, so it's not unexpected to get different results than the RC formula provides. I didn't realize until later that the frequency isn't quite as important as I thought it was, so this was probably unnecessary. But I did verify that the controller can run at full duty cycle and at a higher frequency. But this got me nowhere in getting the supply to work. Damn it. But that's when I had a realization. Remember when I measured the current sense pin? I didn't pay much attention to it at the time, but there was a nearly 700 millivolt DC offset on that pin. So this means there is only 300 millivolts of range before the current sense threshold is hit. But where is that DC offset coming from? So back on the schematic, I think I might have figured it out. So we have our current limit monitor pin here. So this is the original Mitsubishi controller, but again, the pin out is exactly the same with the new one. So in the original configuration, this 390 ohm resistor was actually 75 ohms, and this current sense resistor was actually 0.22. But if you look at this, it's also tied to the B plus voltage, the 163 volts DC, through these two pull-up resistors here. So I've modeled that in LT Spice here. So we just have a very simple schematic kind of reproducing the circuit from the full schematic. So we have our voltage source here of 163 volts DC. Then we have our two pull-up resistors here. Then we have our CS or CLM input for the current source. Then we have the 75 ohm resistor and then the 0.22 ohm current sense resistor. So if I run this now, we see that at the current sense node, we have 130 millivolts or 0.13 volts. And so that's fine for the original controller, and that's way below the threshold for the new controller as well. But now if we change these values to what we have currently installed, So now we have 390 ohm, which is part of the RC filter for the 3844 current sense input. Then we have our 1 ohm sense resistor. Now we run this. And what do you know? We have 675 millivolts at the CS node, which is exactly what we were seeing with the real world test. And for the original controller, this made sense. So these pull-up resistors are here to set kind of a constant power limit for the supply. So as the voltage, the input voltage increases, that's going to actually decrease the headroom there for the current sense input on the original controller. And that's good because it's a voltage mode controller, whereas with our new one, it's a true current mode controller. And so all we're doing by tying it to B+ is just robbing ourselves of current sense headroom. And so it doesn't really make any sense to have that there. So what I'm gonna do is take out one of these 47K resistors, which will sever the link to the B+ supply. So I've created a schematic that shows kind of what that's gonna look like. So we no longer have our B+ reference voltage. Instead, we just have a 12 volt voltage source here. Then we have a current source, which represents the MOSFET source. And so I have just 1 amp coming from this currently. We have our current sense resistor of 1 ohm, and then our 390 ohm resistor, part of the RC filter, and then finally the CS pin on the 3844. So now if we were to run this, we have 1 volt at CS. And so we know 1 volt is our threshold for the current sense limiting. So if we're at 1 volt at the CS pin, that means current limiting is going to kick in. And so what you're really supposed to do is set this value to account for the peak primary current through the transformer. And to know that, you've got to know the turns ratio and some other parameters that we just simply don't know. But from the output, so this power supply can do 5 volts at 9 amps. 1 amp through the primary seems maybe a bit too low. So really the only other suitable resistor I have for the current sense resistor is the original of 0.22 ohm. So let's go ahead and change it to that. And now if we run the simulation, we can see that of course we're at 0.22 volts or 220 millivolts at the CS pin. So that's way below our threshold. Whereas before, if we had had that B+ reference, we would be upwards of near 1 volt, even with this lower current sense resistor. And if we had had the 1 ohm resistor, we would have been, of course, way over it. So if we have this 0.22 ohm resistor, let's set our current to something like 5 amps through the primary just to see. So at 5 amps, we'd be over the threshold for the current limiting, which is good. And I think really what I'm gonna have to do is just sort of play around with the values to see exactly what to get this set at, because you know, we've got to ensure we want to make our rated output, but we also want the current limiting to actually work. So we don't want to have this current sense resistor too low, and we don't want to have it too high, because otherwise we won't be able to reach our maximum output. So it's going to take a little bit of experimentation to get the values right, but I think we might be on the right track. Whoa, is it? Oh my God, I think it's working. It sounds a lot better. Our duty cycle is pretty low, but yeah, because I don't have the current sense grounded, so it's working. Okay, so I think we're really close to being able to actually fully test the power supply with the IPX. There's just a couple of issues still left that we need to address. One is we need to make sure that the supply can actually output full power. So it's rated for 5 volts at 9 amps. And so to do that, we're going to need to connect some power resistors to the output and see how high we can get. And then the other question is the current sense resistor. So currently we have the 0.22 ohm resistor in there, which is the original. And I'm a little concerned it might actually be a little bit too low. And the danger there, of course, is that if it's the wrong value, then we might not be tripping the current limit protection until we get into like 10, 11, 12 amps, which could end up like damaging the transformer or other components on the power supply. And so what we need to do is monitor the current sense input to see how close to that 1 volt threshold we get. And then from there, we should be able to figure out what value resistor we need for current sense. So if both of those things end up working out, we should be able to put it back together and actually test it with the IPX finally. So let me go through and explain the setup we have here, because there is a lot going on. So we have the power supply here, of course, and I've got the fan hooked up to it, and I've got the oscilloscope monitoring the current sense pin here for the new controller. And then for the load, we've got a terminal block here, and I've got two 4 ohm power resistors here hooked up right now, which should give us an equivalent of around 2 ohms. And to actually be able to monitor the current draw, I've got the multimeter here set up in series with the output. And so we'll be able to see on the multimeter how much current we are consuming. And I believe, yeah, this one only goes up to 10 amps. So we're gonna be pretty close to the limit, but I think we'll be okay. And so to actually achieve 9 amps, we need a little bit over half an ohm of resistance. And so I've actually got one of these here. This is like an automotive resistor pack that you'd use for like a blower motor. And so it's got this nichrome wire here and several different windings that offer us different resistances. And I think we can use one of these to get pretty close to our target amperage. There's going to be quite a lot of power going through here. So I've got a fan set up here. These shouldn't get too hot. I mean, they will get hot, but not too bad. And so while, as soon as we connect this, I'll, pop this fan on, and then, that hopefully should keep that cool. So I think, yeah, let's go ahead and start out with the 4 ohm resistors here. So about 2 ohms, and just make sure that our setup works and that, we're able to monitor everything. And then if all that looks good, then we can move on to the big test. Okay, so I think we are ready to test. So I'm gonna go ahead and turn the supply on, and we should see around 2.5 amps on the multimeter here. And yeah, we do, so that's great. Yeah, it seems totally steady. And then if we take a look at, it's around 630 millivolts, something like that. So yeah, I think we're ready to move on to a next test with the higher amperage. So I'm going to go ahead and get one of these coils hooked up, and then we'll see what happens. So we're at 4.58 amps, and we're seeing around 720 millivolts on the current sense. So that looks good. So it says we're only at about a little over 6.5 amps, but we're seeing, a little over 900 millivolts on the current sense. So that's pretty good. Okay, I think I've got it set up correctly now. So I've got 2 coils here hooked up, and I think we should be right at the 9 amp limit, a little bit below it. And so if we run okay here, then I'm ready to give this the okay. So let's go ahead and switch it on and see what kind of amperage we get, and if everything seems like it's running okay. Yeah, so we're at dropping 8.45, 8.44. And we're just around a volt there. So actually, it looks like I think we've got this set up correctly. So I think we're good. So it's running pretty much at full tilt here. Plus, I'm not accounting for the fan. So that is actually consuming a little bit of power as well. Not a ton, but a little bit. Yeah, I think we're okay. I had to try one more resistor combination, and we finally got up to the rated output. The current sense pin is showing a lot of timing variance though, and this might just be the current limiting in action, or it could be something going on with the feedback, but we're right at the 1 volt limit. And our duty cycle increased to 25%, so with this frequency, that looks good. And I almost forgot, we need to double check the output voltages at this high load to make sure that everything's being regulated correctly. So I've got everything set back up, and I will turn on the supply now. Yeah, around 5.1, that's good. And then we'll check the 12 volts. Okay, let's try this again. I had to put the supply on its side. Yeah, I think we're good there. A little over 12. And then our negative 12. It's also good. And I think that should be about it. My main concern was whether the current sense resistor was correct, meaning it had the correct value, and I think it does. I mean, based on what we saw from the current sense pin, we saw the voltage, start out relatively low with a lower output, and then as we increase the output, we saw that voltage level rise, and right around the max rated output, around 9 amps, we saw the current sense voltage right around a volt. So I think that worked out great, and I think really the only thing left to do now is put it all back together and actually test it out with the IPX. I think everything should work, and I'm really excited to see whether the IPX will actually work or if we're gonna have to then go down a huge rabbit hole on that. But this has been a massive learning experience for me because when I started out, I kind of knew the basic theory and operation of a switch mode power supply, but had never done anything like this, like implementing a new controller for it. And though I had a lot of help along the way, this is really how I learn best. I need projects like this where I can have an end goal and actually do something, and there's still plenty left to learn, but I'm really happy that this ended up working out. And so we're actually going to be posting the schematics and PCB layout on our GitLab page. And so if you've got one of these supplies and you want to try to get it repaired and you think maybe the controller is at fault, hopefully this will help. And this might be something we even sell as a kit, so we might be able to put these boards together for you and then kind of sell it as a kit along with the parts for the main power supply. But anyway, all that being said, let's go ahead and get this reassembled and test out the IPX. So it lives. The IPX has finally powered back on after who knows how long. But then I started to smell something. So I decided to open up the case again to see if something was beginning to fail.
Jesus Christ.
Thanks for watching the Parallel Port, and we'll see you next time.